Hi, I'm Dr. Brian Mendez, the Planetarium Director at the Lawrence Hall of Science at UC Berkeley. The Mount Nose activity is a very simple but effective way for you to model how day and night happens in the classroom. All you really need for it is a light bulb that can stand in for the sun, and then your students will act as the Earth itself. You'll want to get that room as dark as you can. The darker, the better. And the closer you can get the students to the light source, the better. That helps create the big difference between light and dark. So in this case, what works best is actually an incandescent bulb because it produces kind of the best light for this. You can get by with a very bright LED bulb, but the incandescent bulbs without any coating are the best. You'll of course want to have a lamp that you can plug the light bulb into, along with a clamp. If you can get yourself a nice stand to put it on, any tripod for a camera will work. And then of course you'll want to plug this into some kind of extension cord. And so you'll want to just be careful to tape it down with some gaffing tape. A gaffer's tape works well because it comes up really cleanly. This light bulb in the center of our circle is representing the sun. Okay? What ways is it like the sun?
Bright.
It's bright? Okay. What other ways is it like the sun?
It's in the middle of all of us.
It's in the middle? Oh, okay. Like the sun is in the middle of the solar system? Sure. Are there some ways in which it's not like the sun?
It's very close to us.
It's very close to us, right? Yeah, the sun is pretty far away. What other ways is it different from the sun? It's very small, right? It's very, very small. The sun is huge. We can fit 1 million Earths inside the sun. So how is the Earth different from our heads?
Much smaller in relation to the sun.
Right, yeah, we've got this kind of scale thing going on here where our heads are bigger than our model sun, but it's the opposite, right? We could fit 1 million of our heads inside a model sun. One of my favorite things to contemplate is if we were to make a model that accurately represented every single aspect of a system, it would be the system itself. Right? So a model always, by necessity, has to have something in which it's not like the original system. But this is going to work for us to demonstrate day and night. We've got our heads being the Earth. We can imagine that the top of our head is like the North Pole of Earth, and that our necks are like the South Pole of Earth. Okay? And then we're going to imagine that our noses are a big old mountain on the equator of Earth. And we're going to call it Mount Nose. Everyone right now, let's face the sun. You don't have to stare directly at it, but let's face the sun, point your nose at the sun. What time of day would it be if you were standing on Mount Nose and the sun is directly over your head? What time of day do we commonly think of that as?
About noon.
That's right, noon. So we're at noon at our nose, but the Earth doesn't stay stationary, right? The Earth spins. And so we want to add spinning into our model. And does anyone have a sense of what direction the Earth spins in? Does it always spin in the same direction?
Yes.
It does always spin in the same direction. Any sense of which direction the Earth spins in? Yeah, it's not too easy to know it right off the bat. So I'll just tell you that in our model where our neck is the south and the top of our head is the north, spin would be to our left. And that is defined as the direction east. So east is the direction in which the Earth turns. So if we think about our face, we'll think about our ears. We've got a left ear and we've got a right ear. So if our left ear is east, what direction is the opposite of east, our right ear?
West.
All right, so I'm going to call this East Lake Erie and West Lake Erie. So we got a couple of big lakes, okay? So we're going to now model spinning a little bit to the east. And we're going to move just about a quarter turn. So we're going to spin. So go ahead and start spinning a little bit. And I want you to spin just to the point where the sun starts to almost disappear from your view. It's right on the edge of disappearing. All right, so everyone reached that point? Great. All right, so the sun is just about to disappear. If you were to continue just a little bit longer, it would disappear, right? And what direction is that? This is our right, where the right ear is. That's the west. So the sun is about to disappear over the west. Does anyone know what the name of that time of day is?
Sunset.
That is right. This is sunset. So this is the end of the daylight hours for Mount Nose. However, let's think for a moment about West Lake Erie. Where is the sun in relation to it? It's right above it, yeah, at noon. So that's interesting. It's still noon at some place on Earth, but the sun is setting for us on Mount Nose. Let's now continue with our model, and we're going to spin a little bit further so that Mount Nose is pointed directly away from the sun. What time of day now is it for Mount Nose? Is the sun anywhere in Mount Nose's sky?
Nope.
No, so it's nighttime, right? And since we're directly pointed away, it's kind of the middle of the nighttime. So what do we call that? We call it midnight. Great job. Now think again about West Lake Erie. What's happening there? Where is the sun in relation to West Lake Erie? Right. It's just about to disappear out behind its horizon, right? So that is what time of day? It's sunset. So for West Lake Erie, it's sunset. And for Mount Nose, it is midnight. How about the backs of our heads, which we'll call the dark forest, right? What time of day is it right there when the sun is directly above the dark forest? It's noon. So we start to get this sense, right, that the time of day depends on your relation to where the sun is. Let's keep spinning one more quarter turn so that the sun is just about to appear over the horizon from the perspective of Mount Nose. What time of day is it on Mount Nose now? The sun is rising. So what do we call that? Sunrise. Good job, everybody. Yes, sunrise. So we've got sunrise at Mount Nose. What time of day do we have for West Lake Erie? Midnight. Great. And how about for the dark forest? Sunset. Great. Let's continue on and go back to noon at our nose. All right, so it's noon in Mount Nose. What time of day is it for West Lake Erie? Sunrise. How about for the dark forest?
Midnight.
And how about East Lake Erie? Sunset. So look at that. We've got all the times of the day represented as a circle around our head. And everywhere is experiencing that different time depending on where they are. And the motion of spinning is what actually took us through those times, right? The actual movement of our spinning is what changed the time of day. So now we've got a sense of what causes day and night, right? We've got the side of the sun, the earth that's facing the sun, that's daytime. We've got the side that faces away from the sun, is nighttime. Thanks for joining us for this video tutorial about how to do the Mount Nose activity with your students. If you'd like to do an additional extension where you bring the moon into the equation and learn how the phases of the moon occur, you can watch an additional video that we have for that. Also, you can check out other activities to teach about space science at the Space Weather Explorers Week website, the links of which are posted in the description below.